Hi there, welcome to this course on design patterns. I am Rangarao Karnam and I have more than 15 years of experience designing, architecting and developing Java applications. In this course, I would want to give you an introduction to the world of design patterns. In my experience, I have seen more instances of design patterns being abused compared to design patterns being properly used. You might ask, why this course? The objective of this course is not to teach the implementation details of each design pattern, not far away from it. What we want to understand in this course is the context in which a particular design pattern might be applicable. We would discuss these with real world examples. If you are familiar with what we do in 28 minutes, this course would be a deviation. Typically, our courses would be 90% hands-on and 10% theory. In this course, we would really want to focus on the context of each design pattern. We would be talking about three different types of design patterns: creational, structural, and behavioral. There are about 23 different design patterns which are present, so we would be talking about each one of them. A little bit of programming experience with Java might help you. We don't really consider it mandatory. A huge percentage of the course, you don't really need any technical experience at all. We are really excited to bring this course. If you are as excited as we are, go ahead and click that enroll button. Or you can take a test drive using the free preview feature. See you in the course. What are design patterns? We have been building object-oriented software for almost 40 years now. Smalltalk was the first object-oriented language. The programming world has encountered a lot of problems and they have tried a varied range of solutions for them. Some successful, but some not so successful. An attempt was made by a group of 4 people, famously called the Gang of Four, to come up with a list of common problems and the solutions for them in a given context. And this catalog of common problems and their solutions are what are called design patterns. The advantages of design patterns are quite clear. You don't want to repeat the same mistakes again. Whatever has been learned, if we have a good understanding of design patterns, we would not repeat those mistakes again. There are 3 different kinds of design patterns. The design patterns which we are talking about are from the perspective of an object-oriented world. So we are really restricting ourselves to the gang of 4 design patterns. And the types are creational patterns, structural patterns, and the behavioral patterns. Creational patterns deal with the complexity associated with creating objects. Object-oriented programming is full of objects. There are varied kind of objects that we create with varied range of problems. And these creational design patterns deals with how you can create them. What are the options you have? The structural design patterns, on the other hand, deal with the composition of the classes. What does a class contain? What relationship does it have with other classes? Does it have an inheritance relationship? Does it contain the object of another class? All these kind of design patterns are grouped under structural design patterns. The last category of design patterns, the behavioral design patterns, is more focused towards the behavior of the objects. That's basically the interaction between the objects. How does an object communicate with another object? And all these kind of patterns fit in this category called behavioral design patterns. In the next series of videos, we would be looking at each of the design patterns in these categories in detail. We would start with the creational design patterns. We will start with the first of the creational patterns, which is the prototype design pattern. If you look at the prototype design pattern, it says a fully initialized instance to be copied or cloned. A lot of the definitions of the design patterns might seem very complex at the start, but when we really understand them with an example, you would really see that they are very simplified definitions. Let's consider a game of chess. In the game of chess, there is an initial setup of how the pieces have to be arranged. The king is in a specific place. The pawns are in specific places. Queen, rook, bishop, everything has a place that is assigned to them. So let's say I'm building a software to model the chess game. Every time a new chess game is played, I need to create this structure again and again. The initial layout of the board, I would need to keep building it again and again. Instead of doing it again and again, can we have an object of that build and have it readily available so that whenever we need to create a new chess game, we copy from it or we clone from it? That's the prototype pattern. In a prototype pattern, you have a fully initialized instance. The fully initialized instance in this particular context is the initial setup of the board. So the initial setup of the chess board, you would have it fully initialized and available. Whenever a new chess game is started, let's say take the online website chess.com. There are thousands of games being played every day. I mean, actually, millions of games played every day. And every time, what they do would be to copy the initial structure that they have. They would not keep creating the structure of the board again and again. Whenever a new game is initialized, you have an already initialized instance and you copy it. In the technical terms, that's called cloning. So you clone the already initialized object, and that's the prototype pattern. Builder pattern is the second of the creational patterns that we would be discussing in here. The builder pattern separates object construction from its representation. What does that mean? I go out for a multi-course dinner. There would be a lot of options which are present: drinks, starters, main course, dessert, a huge number of options. And probably I would choose 2 or 3 of them. A similar kind of situations arise in software as well. You would need to build objects using 2 or 3, I mean a subset of the ingredients which are present. Somebody might need a multi-course dinner with a drinks, starters and main course. Probably they would want to avoid the dessert. Somebody else might want a drink, they want to skip the starters, they would directly want to go to the main course and the dessert. So there are multiple ways people would want to organize or to have their multi-course dinners. If I'm representing this in software, then I would need to be able to create the object in multiple ways. Sometimes I would need to have only 3 ingredients, sometimes only 2 ingredients, and sometimes only 1. And that's where the builder pattern comes in. To understand the builder pattern further, we would look at a small piece of code. If you're not familiar with the technical details, probably you can skip this. You can kind of try and understand and try and make sense of what's happening in here. The example which we are looking at right now is from our Git repository. In 28 minutes, design patterns for beginners. So you can find this example in there. You can just search for builder pattern and you would be able to come in here. The example which we took was trying to build a coffee. If you are from India, then you would always have coffee with milk. And if, let's say, you are in United States, for example, most of the people prefer having coffee without milk. You would want to be able to have multiple options of how you build your coffee up. And that's where the builder pattern comes in. If you look at this particular piece of code, what we have is a builder. To the builder, we pass in the mandatory things. So the type of the coffee that I want is mandatory. I mean, that's the basic. And after that, we add in whatever we want. So I'm building a mocha with milk. I'm saying milk true. That's with milk, with no sugar and size large. And I'm building the object and now I have my coffee ready. If somebody else wants a different flavor, they can easily build it. So now somebody else who wants coffee with milk and sugar can come and say coffee.buildermocha.milktrue.sugartrue and size large .build. Thereby, you have a huge amount of flexibility in building the objects. Other approaches to doing this other than using a builder pattern, but using things like setters have a lot of problems associated with them. They result in very difficult code to read as well as they have a few problems in threading. We'll not go into depth with those. The builder pattern solves all those problems. The important things about builder pattern are that it simplifies the creation. This is very simple code to read, and also this is very easy for a developer to write code with. If you are interested in understanding how the builder is built, you can look at the public static class builder. You go for a builder pattern when you would want to have multiple options in creating a particular object. A builder pattern separates object construction from how it's represented, and it makes it very easy to build objects. Third in the creational patterns, which is the singleton pattern, is the most famous of all the design patterns, I guess. What the singleton pattern does is very clear from its name. It's a singleton. There can only be a one instance. So for a singleton, at any point in time, there can only be one instance. I mean, a good real world comparison would be probably a president of country. There can only be one president for a country at a particular point in time. Just like that, there can only be one instance of a singleton object. However, there's a disclaimer. Actually, when we say something is a singleton, it's actually one instance per JVM. So let's say if I have an application which is running as part of a cluster in multiple application servers, then you would have one instance in each of the application servers in that cluster. So to be really specific, singletons are actually one instance per JVM. For the rest of the discussion, we'll kind of talk as if it's only one instance can exist. So a class of which only a single instance can exist. That's your singleton. There are a few things that you need to remember when you create a singleton object. The first one is your constructor should be private, because you don't want others to create the object. I mean, if you leave a public constructor, then what would happen? Anybody can construct the object, and then you don't really have a singleton. So you have a private constructor. The best way to build a singleton in Java is using an enum. It is recommended in the book Effective Java as well. You can find a sample singleton using enum on the GitHub repository. It's very simple to use an enum to build a singleton. All that you need to do is create an instance, make your constructor private as usual, and then you can create the methods which can be called. So this would be my singleton using enum dot instance dot retrieve something. So it's as simple as that. And if you're using JEE 7, there is a built-in add singleton annotation. So you can probably check that out. Okay, now we have talked so much about singleton, but are there any disadvantages? Yes. Singleton makes it very difficult to unit test. So if you have a lot of singletons in your application, this application would be really difficult to unit test. Make a clear decision as to where you want to use these singletons and where you don't. The last thing we want to talk about is the fact that in frameworks like Spring, we manage beans, and these beans are singleton by default. But what Spring does very well is the fact that these beans don't need to be declared as singletons. I mean, if you look at the code for these particular beans, you will not realize that they are singletons. This is kind of taken care by Spring in the background. If this technical discussion sounds little complex to you, don't worry about it. All that you need to know is a singleton is something of which there can only be one instance. Let's quickly move on to the next design pattern we are going to discuss about, which is the factory method design pattern. If you look at the definition of factory method, it says create a family of object types. So let's quickly look at an example. I mean, factory method is not complex, so just look at an example. We should be able to understand it very quickly. So here we have a person factory method. What we are doing, I mean, not a method, actually person factory class. So this person factory has a static method get person, and this accepts gender as one of the inputs. So if you pass in M, it returns a class of type male, and if you pass in F, it returns a class of type female. But as far as the classes which use this person factory are concerned, the only thing they know about is person. So if somebody wants to create a male person, what they do is they say person male is equal to person factory dot get person, and they pass in M. And to create female, they would pass in f. So basically, they would pass some identifier of the type of the object that you want to create, but they would still be referring to the generic type. So we have a person and male extending person and female extending person. The fact that there are male and female objects existing are hidden behind the implementation of the factory method pattern. So whoever is using this particular factory only knows about person, but they don't really know about the existence of a male or a female class. The benefit the factory method pattern offers now is the fact that you can add additional types of genders or additional types in here without affecting whoever is using it. So whoever is using it is only using person. So they don't really care about whether male, female, or whatever. You can have different implementations for the same methods in those objects as well. So if you look at the get salutation, you have written Mr. here. Here it is Miss or Mrs. So based on whether it's a male or female, if you call the get salutation, you'd get a different thing. So that's basically the benefit of the factory method pattern. What it hides is the complexity in creating an object. So instead of somebody else deciding whether you have to create a male or female, we have a factory making the decision for us, and at a later point in time, whenever we want to modify this, it becomes really, really easy. So that's the factory method pattern. Let's move on to the structural design patterns. The first of the structural design patterns that we are going to talk about is the proxy. The definition of proxy says an object representing another object. I have a debit card. Whenever I make a transaction using a debit card, where does the money go from? The money goes either into my bank account or out of my bank account. So whenever I'm swiping my debit card somewhere, what I'm doing is I'm using the debit card as a proxy for my bank account. So the actual object is the bank account, and the debit card is kind of a proxy for it. So whenever I make a purchase, I swipe it, what is actually happening is the money is deducted from my bank account. Debit card is a proxy for it. Similar to that, in programming, you have a lot of interactions with remote objects. Let's say I'm talking to an object which is in a distributed system somewhere outside my system. What we would do in such cases is create a proxy object. So what the proxy would do is proxy would take care of all the external communication. As far as I am concerned, I would be talking to the proxy as if it's something which is very near to me. The good example for that are the EJB home and remote interfaces. A proxy is basically an object representing another object. Proxy hides the complexity in communicating to the real object. The second structural design pattern that we would be talking about is the decorator pattern. In the decorator pattern, we would add responsibilities to objects dynamically. What does that really mean? Typically in the object-oriented programming, we use a lot of inheritance. Let's say I have 10 types of pizzas. So pizza type 1, pizza type 2 to pizza type 10. And now there is a new requirement. I need to make these 10 types available with 3 different types of toppings. I would want pizza type 1 with topping 1, pizza type 2 with topping 2, pizza type 3 with topping 3. I already have 10 types, so if I add 3 of each for these 10 types, then I would have 30 different classes to manage. Inheritance is kind of a static relationship. So instead of doing this, can we make it dynamic? Can we add the topping on top of an existing pizza? So you have a pizza and kind of use the topping as a decorator on top of it. So that's the concept behind the decorator design pattern. So instead of creating multiple types of the same object again and again, can we add the additional responsibilities dynamically as kind of a topping? A good example would be also adding a discount and an order. I already have an order and I would want to add different kinds of discounts on top of the order. For example, in India we have this thing called Paytm and they have a lot of discount offers. If I keep adding different types for each of the discount, I would have hundreds of classes to maintain. So what they really do, they would would be to add the discount as a decorator on top of the existing order. A very good example of decorator pattern in Java is the Java IO. So the way we create the input streams. So I have a file input stream. If I want to make it buffered, I would need to create it as buffered input stream and pass the file input stream as a constructor argument. If I want to read it in lines, if I want to add a line number on top of it, the way I would need to do it is line number input stream and pass the buffered input stream as input to it. So this is how things are in Java IO. This is the implementation of the decorator pattern. You can actually look up the code for line number input stream to see how decorator pattern is implemented in there. The thing about the decorator pattern is it helps in adding runtime behavior. So you are adding behavior at runtime. So the user of the interface can decide how he wants to create the objects. But that's also the complexity. So somebody who needs to use the decorator pattern needs to understand the different structures which are present. So it will not be a simple create pizza type 1 topping 3. It would not be as simple as that. So there would be a little bit more complexity to it. So there would be a little bit of complexity in creating the objects. That's the disadvantage of the decorator pattern. So basically, the decorator pattern is all about adding responsibilities dynamically. The next pattern we would be looking at is the facade pattern. The definition of the facade pattern says a single class that represents an entire subsystem. Let's take the example of an event manager. I want to organize an event. What I would do is I would talk to an event manager and tell him, I need this kind of decoration, I need this kind of food, I would need to send invitations to all these people, this is the kind of music I would want to arrange. And the event managers would take care of everything for me. So these good event managers are very good examples of facades. So anytime I want to do something, I would talk to the event manager and the event manager would organize that for me. Similarly, when we are talking about a distributed system, you would have the need for multiple calls across layers. For example, let's take the example of an online book order. So if I'm making an order, there are a lot of things that we need to do. First thing is we have to check whether there is stock and then reserve the book. The next thing is we have to make the payment, update the stock and generate the invoice. So if the client interface has to handle all of these individually, there will be a multiple set of calls which would be going on and in and out. So rather than that, what we would do is we would create a single facade, single interface which would handle everything. So the client would give all the inputs to this facade and the facade would take care of making all the calls for us. The advantages of the facade are that you would reduce the amount of network calls and also you would reduce coupling. So how the facade works is separated out. So the facade, as long as the interface remains the same, the internal details of the facade can keep changing. And also one more important thing is the facade kinds of represents the transactional boundary. So if you are technical and if you understand transaction management, some of the times facades or services are good places to implement transaction management around. So that's your facade pattern. The adapter pattern is used to match interfaces of different classes. What does that mean? Let's take the case of power adapters. Let's say I buy an iPhone in India. It comes with an Indian charger. Something which fits with the Indian electrical system. And when I go to US, it won't work because the power adapters in US have different kinds of a pin configuration. So what I do is I would take an adapter. So when I'm going to US or Europe, I would buy a power adapter to which I would plug in and I would use the power adapter to connect to the line. Similar to that, when I'm talking to a different system and the language used by that system is little different, I would need to have an adapter to modify what I'm sending to the format which is understandable with this second system. A good example is probably the conversations between a Java and let's say I'm calling a web service. Before I call a web service from my system, I need to convert the object into an XML or a JSON. this is nothing but an adapter pattern, because way Java systems work is based on objects. But the web service expects a JSON. So what I would do is I would convert the object into a JSON and send it to the web service. And that's kind of an adapter. The last structural pattern that we would be talking about is the flyweight pattern. There are instances where creating objects might be very difficult, and also there would be instances where actually having multiple instances of objects also might make it really difficult, because each of these objects might have a lot of memory. What we would be creating in the flyweight pattern is a fine-grained instance for efficient sharing. A really good example would be a public switched telephone network. In a public switched telephone network, there would be limited number of lines. So let's say there are 10 lines, but there would be thousands of customers who would be using them. Because not all the 1,000 customers would be calling at the same time, you would be able to try and switch between these 10 lines and efficiently manage the network. A real good examples of flyweight patterns are JDBC connections. In the JEE world, we have a lot of connection pools on the application servers. A connection pools is nothing but a set of connections to the database. From the application, we fire in a lot of queries, but we don't create a connection every time a new query comes in. What we do is we have a pool of connections already available. Let's say we have a pool of 20 connections already available. So as soon as a query comes in, we match it to a connection, and then the query gets fired. And once the query completes execution, the connection gets released. So we have a pool of connections, and this pool of connections will be used to execute the queries. This would help us in avoiding the cost in creating the connection and closing the connection to the database every time. So we would kind of have a shared pool of connections. That's a very good example of the flyweight pattern. So basically, flyweight pattern is all about creating instances for efficient sharing. Let's now move on to the behavioral patterns. The first behavioral pattern that we would be talking about is the chain of responsibility patterns. The best example for chain of responsibility patterns is an exception handling mechanism in most of the programming languages. Let's say I have a method 1 calling method 2 calling method 3, and the method 3 throws an exception. If there is no exception handling in method 3, then the programming language looks at method 2 to see if there's some exception handling, some try-catch block. Nope, nothing is there. Then it would go further up and further up and further up. That's a very good example of the chain of responsibility pattern. The way chain of responsibility pattern is defined is a way of passing a request between a chain of objects. Let's take a loan approval process. The clerk at the bank has permissions to approve loans up to a certain amount. If the amount goes above that, then his supervisor comes in, and there's a limit for him, and then the supervisor comes in, and so on. So this is a kind of a good example of a chain of responsibility as well. In a chain of responsibility design pattern, what happens is we have a set of objects or a chain of objects which are already ready. I mean, these chain of objects handle the approval process, for example. And whenever a new request comes, I would go to the first object in the chain and check, will you be able to approve? No. Then I would go to the second object in the chain, and then the third object in the chain, fourth object, and so on. So that's basically the chain of responsibility pattern, where a request is sent to a chain of objects until it's hatched. The iterator pattern is kind of the most simple of the design patterns. You have a set of items and you would want to loop around them. So the iterator pattern defines a way where you can loop around the objects in a collection. So it's defined as sequentially access the elements of a collection. A good real world example of an iterator pattern is the next previous buttons on a TV remote. As and when I keep pressing the next button, I would be switching to the next channel, and so on. A good example of iterator pattern in Java is the iterator class itself, And also we have now the enhanced for loop and things like that, which help us to loop through the collections. The definition of a state pattern says alter a object's behavior when its state changes. What does that mean? Let's discuss with an example. Let's take the example of a fan wall control. For example, in India, we have these fan wall controls with different levels. So, if the fan wall control is at level 1, the fan rotates at a certain speed. And let's say if it's at level 5, it rotates at the maximum speed possible. When I rotate the knob, when I rotate the fan wall control knob from level 1 to level 2, there is a change in the behavior of that particular object, which is the fan. So the fan rotates faster. State of the fan wall control right now is level 2, and I call a rotate method. The state goes to state 3, and if I do again a rotate, the state goes to state 4. So depending on the earlier state, the next state is decided. So in these kind of situations, we represent the state of the object as a separate class. Let's see a quick Java example. What we have is a static class, which is a fan wall control with a speed level composed in it. So this fan wall control has the speed level in it. Speed level is an interface which has 4 different implementations of speed level 1, 2 and 3. And if the fan is off and I click a rotate, what it happens? The new state changes to speed level 1. And if it's speed level 1, I do the rotate, it goes to speed level 2. Speed level 3, I would go to from 2, I would go to 3. And from 3, if I do it again, I'll go to off. So this is kind of an implementation where we are actually pulling off the state of the particular thing. So the state is the current speed level. So speed level 1, speed level 2, speed level 3 are different states in which the fan wall control can be. What we are doing is we are making this state a specific class on its own, and thereby the fan wall controller does not need to know about what the current state is. So it just says speed level current, and whenever somebody calls rotate, it delegates the rotate call to the speed control. So thereby what happens is if I add in a new speed level, all that I need to do is define a fifth speed level or a fourth speed level and implement the rotate method. This is a very good example of having extensible classes. In the example which we looked at, based on the level at which that particular object is in, the behavior changes. So if it's at level 1, because we are now switching to a different implementation of that interface, the behavior changes. Let's move on to the next pattern, the strategy pattern. Strategy pattern encapsulates an algorithm inside a class. Let's look at a Java example. I have a very complex class. There is a lot of business logic in it. And one of the important things which it needs is it needs to be able to sort a set of items, sort a set of numbers. One of the ways we can implement is we can directly implement the entire logic for sorting in there. Tomorrow, if I want to change the sorting, then I would need to change the implementation of that particular complex class. Instead of that, what we can do is we can use a strategy pattern. In the strategy pattern, we kind of separate the algorithm of how the sorting is done from the complex class. What we do is we are creating here an interface called sortable. And we have a couple of implementations of the sortable interface, bubble sort, quick sort. We don't really have the implementations in here, but you can assume that bubble sort is implemented in here, it's quick sort in here. So thereby, this complex class, all that we need to do is we need to pass in what sorting algorithm to use. This will not worry about how the sorting is done. All that it expects is some kind of a sorting algorithm as an input. And later, it would use that sorting algorithm to sort. And when we are creating the complex class, to the constructor, we would pass the exact algorithm to be used as an input. So the users of the complex class can decide what sorting algorithm to use. So there's a lot of flexibility that comes in because of using the strategy pattern. Basically, you can dynamically keep changing the strategy and see the right one for your particular context. The next pattern we would want to look at is the observer pattern. Observer pattern is a way of notifying a change to a number of classes. So, what does that mean? Let's say I would want to know whenever Sachin scores a century. And there would be a lot of people like that. They would want to know when Sachin scores a century. What they would do is they would say, I would want to register. So they would all register as observers. And whenever Sachin scores a century, this centralized program will notify all the observers. So I will know when Sachin scores a century. It's kind of how it happens in online bidding as well. So you'd say, I would put a bid. I put a bid, and whenever there is a bid higher than whatever I have done, then all the bidders would be notified. So there are really two important parts to any observer design pattern. One is the registering part. So I would want to register as an observer. And the second one is the notification part of it, where I would be notified whenever there's a change in the in the object which is being observed. I would need to be notified that there is a change. That's basically the observer pattern. A simple example of the observer pattern is on the GitHub repository. What we have is something called a Sachin Century notifier, and what we are saying is we would want to register 3 fans. So we are registering 3 different fans, and whenever there's a Sachin Century scored, notifier.Sachin scored a century would be called, and all of us would be notified. So you would see that the output of the program is that all of us are notified. So you can take a quick look at this to understand the observer pattern. Observer pattern is quite a simple thing. It's a way of notifying the change to a number of classes. The next pattern we would want to look at is the visitor pattern. A visitor pattern defines a new operation to a class without change. There are a lot of situations when we are designing frameworks that we don't want other people to modify the code of the framework. So basically we want others to be able to extend the functionality without touching the code inside the framework. In those kind of situations, we would want to allow them to add new operations, but we don't want to allow them to change the code underneath. And that's where the visitor pattern comes in. The implementation of visitor pattern is a little tricky thing, so we would really stay away from it. A good example for a visitor pattern is the operation of a taxi company. As soon as a person calls a taxi company and the company dispatches a cab to the customer, we are accepting a visitor. So the cab company is accepting a visitor, that's the new customer. Once the visitor has entered the taxi, so once the customer enters the taxi, he is no longer in the control of where he is going. The driver of the cab is now in the control. So the visitor would be now in the control of another class who is the driver. And the driver can add new operations on top of the visitor. Kind of a good example of the visitor pattern. Typically, when you are in a situation where you're building a framework and you want somebody to be able to extend it or add new operations on top of it, but you don't want them to be directly modifying the code of the framework, in those kind of situations, you can consider visitor pattern as an option. The next pattern we are going to look at is the template method. Template method, the pattern definition says, defer the exact steps of an algorithm to a subclass. What does that mean? A good example is again a house plan. Basically, any house plan would consist of a foundation, pillars, a floor plan, framing, wiring, and a lot of other stuff. So you can kind of create a basic template class which has all this behavior defined, and a subclass can extend this and give real implementations for some of the details. A good example of the template method is inside the Spring framework in the class abstractController.java. If you go further down, there is a handle request which handles the request. However, you would see that it takes care of the basic things. It checks the request, it prepares the response. That's basically this sequence of things it does, and at the end it leaves the implementation of the actual handling of the request to the subclasses. So the subclasses can now go ahead and implement the handle request internal method, and thereby they get all the functionality they would need. So a template method is all about taking care of the high level details and leaving the low level steps to the subclasses. The subclasses can override these steps or provide their own implementation for these particular steps. The command pattern is defined as encapsulate a command request as an object. Let's take a real world example. Let's say I'm going to a restaurant and I give an order to the waiter. What does the waiter do? He just writes the order I'm giving on a piece of paper and he would pass it on to the chef. The chef would execute the order and pass the piece of paper down to the waiter. This piece of paper is the command object. So this is the object which contains all the details that are needed to execute that request. So even in object-oriented programming, whenever we have requests like this, we can encapsulate all the things that are needed to execute a request as a single object and pass it across. For example, we have in the Java EE, we have an object called request. Whenever user types in any details on the screen of a web application, all these details are captured in a single object called a request, and the request is sent down to the controller or the servlet. A good example of command pattern is also the runnable interface in Java. We create threads in Java by extending the runnable interface. So when we create a thread, all the functionality of the thread is in this particular class, and we would pass this class and call the start method to invoke all the logic which is present in there. This is a very good example of the command. The next pattern which we are going to discuss about is memento pattern. We are almost at the end of the behavioral patterns, and the memento pattern is basically all about capturing and restoring an object's internal state. A lot of games that we play offer this feature of intermediate save. At a certain state of this game, you can save it and come back to it. To implement such kind of a functionality, we would need to store internal state of the objects at that particular point in time. What we can do is we can store this internal state using something like serialization in Java, and at a later point restore back from it. And this pattern is called a memento pattern. A memento pattern is very much useful in undo redo operations. For example, let's say I'm working on a user interface and I've done a lot of changes. I would want to undo them. As soon as I keep undoing them, I can actually restore back to a previous state if I captured the earlier state. So that's a memento pattern. The last pattern which we are going to look at, a mediator defines simplified communication between classes. Let's take the example of a air traffic controller. At any point in time, let's say in India, we have about 500 flights flying. Let's say we want to decide the routes each of these flights have to take. We have to decide also when they have to land, which route they have to take, when they have to start flying, and all that kind of decisions. If all the 500 flights have to talk to each other and make these decisions, then you know how complex it might be. It gets very complex. That's why we have somebody called an air traffic controller. So the flights talk to the air traffic controller, and based on all the information it gets from all the flights, the air traffic controller can take a decision as to which route a flight can take, when it can land, what time it can start flying, and all that kind of stuff. So all the logic is now with the air traffic controller, and it kind of becomes the centralized thing which decides everything. And it also simplifies the communication between flights because they don't really need to talk to each other. They just need to talk to the air traffic controller and they can get details about all the other flights. So that's basically the air traffic controller. A good example of mediator pattern in typical enterprise applications is the ESB bus. So we use something called an enterprise service bus. Instead of letting the applications talk to each other, you'd have an enterprise service bus where application, all that it does is it puts a message in the ESB and somebody handles it and gives it a response back. It does not really need to care about who is handling it and how it's getting the response back. It's a good example of the mediator pattern. So that's all the design patterns that we wanted to discuss during this course. Congratulations! You have heard about more than 20 design patterns during this particular course. As we said at the start of this particular course, our objective was not to focus on the implementation details. We did not want to worry about the implementation details of each of these design patterns. What we wanted to give you is a flavor of the context in which these design patterns are applicable. And we hope we are successful in doing that. Good luck.